The St. Petersburg Paradox or St. Petersburg Lottery is a paradox related to probability and decision theory in economics. It is based on a particular lottery game that leads to a random variable with infinite expected value but nevertheless seems to be worth only a very small amount to the participants. The St. Petersburg Paradox is a situation where a naive decision criterion which takes only the expected value into account predicts a course of action that presumably no actual person would be willing to take. Several resolutions are possible. The paradox takes its name from its resolution by Daniel Bernoulli, one-time resident of the eponymous Russian city, who published his arguments in the Commentaries of the Imperial Academy of Science of St. Petersburg. However, the problem was invented by Daniel's brother Nicolas Bernoulli, who first stated it in a letter to Pierre Raymond de Montmort on September 9, 1713. The paradox: a casino offers a game of chance for a single player in which a fair coin is tossed at each stage. The pot starts at $2 and is doubled every time a head appears. The first time a tail appears, the game ends and the player wins whatever is in the pot. Thus the player wins $2 if a tail appears on the first toss, $4 if a head appears on the first toss and a tail on the second, $8 if a head appears on the first two tosses and a tail on the third, $16 if a head appears on the first three tosses and a tail on the fourth, and so on. In short, the player wins $2k, where k equals number of tosses. What would be a fair price to pay the casino for entering the game? To answer this, one needs to consider what would be the average payout. With probability 1/2, the player wins $2. With probability 1/4, the player wins $4. With probability 1/8, the player wins $8, and so on. The expected value is thus. Assuming the game can continue as long as the coin toss results in heads and in particular that the casino has unlimited resources, this sum grows without bound and so the expected win for repeated play is an infinite amount of money. Considering nothing but the expected value of the net change in one's monetary wealth, one should therefore play the game at any price if offered the opportunity. Yet, in published descriptions of the game, many people express disbelief in the result. Martin quotes Ian Hacking as saying few of us would pay even $25 to enter such a game, and says most commentators would agree. The paradox is the discrepancy between what people seem willing to pay to enter the game and the infinite expected value. Solutions: several approaches have been proposed for solving the paradox. Expected utility theory. The classical resolution of the paradox involves the explicit introduction of a utility function, an expected utility hypothesis, and the presumption of diminishing marginal utility of money. In Daniel Bernoulli's own words, the determination of the value of an item must not be based on the price, but rather on the utility it yields €1. There is no doubt that a gain of 1,000 ducats is more significant to the pauper than to a rich man, though both gain the same amount. A common utility model, suggested by Bernoulli himself, is the logarithmic function U, W, equals ln, W. It is a function of the gambler a unregistered trademark S total wealth W, and the concept of diminishing marginal utility of money is built into it. The expected utility hypothesis posits that a utility function exists whose expected net change is a good criterion for real people's behavior. For each possible event, the change in utility ln, wealth after the event, ln, wealth before the event, will be weighted by the probability of that event occurring. Let C be the cost charged to enter the game. The expected utility of the lottery now converges to a finite value. This formula gives an implicit relationship between the gambler's wealth and how much he should be willing to pay to play. For example, with log utility, a millionaire should be willing to pay up to $10.94, a person with $1,000 should pay up to $5.94, a person with $2 should pay up to $2, and a person with 60 cents should borrow 87 cents and pay up to $1.47. Before Daniel Bernoulli published, in 1728, another Swiss mathematician, Gabriel Cramer, had already found parts of this idea in stating that, the mathematicians estimate money in proportion to its quantity, and men of good sense in proportion to the usage that they may make of it. he demonstrated in a letter to Nicolas Bernoulli that a square root function describing the diminishing marginal benefit of gains can resolve the problem. However, unlike Daniel Bernoulli, he did not consider the total wealth of a person, but only the gain by the lottery. This solution by Cramer and Bernoulli, however, is not completely satisfying, since the lottery can easily be changed in a way such that the paradox reappears. To this aim, we just need to change the game so that it gives the payoff. Again, the game should be worth an infinite amount. More generally, one can find a lottery that allows for a variant of the St. Petersburg paradox for every unbounded utility function, as was first pointed out by Menger. Recently, expected utility theory has been extended to arrive at more behavioral decision models. In some of these new theories, as in cumulative prospect theory, the St. Petersburg paradox again appears in certain cases, even when the utility function is concave, but not if it is bounded. Probability weighting equals, Nicolas Bernoulli himself proposed an alternative idea for solving the paradox. He conjectured that people will neglect unlikely events. Since in the St. Petersburg lottery only unlikely events yield the high prizes that lead to an infinite expected value, this could resolve the paradox. The idea of probability weighting resurfaced much later in the work on prospect theory by Daniel Kahneman and Amos Tversky. However, their experiments indicated that, very much to the contrary, people tend to overweight small probability events. Therefore, the proposed solution by Nicolas Bernoulli is nowadays not considered to be satisfactory. Cumulative prospect theory is one popular generalization of expected utility theory that can predict many behavioral regularities. However, the overweighting of small probability events introduced in cumulative prospect theory may restore the St. Petersburg paradox. Cumulative prospect theory avoids the St. Petersburg paradox only when the power coefficient of the utility function is lower than the power coefficient of the probability weighting function. Intuitively, the utility function must not simply be concave, but it must be concave relative to the probability weighting function to avoid the St. Petersburg paradox. Rejection of mathematical expectation equals, various authors, including Jean-Laurent D'Alembert and John Maynard Keynes, have rejected maximization of expectation as a proper rule of conduct. Keynes, in particular, insisted that the relative risk of an alternative could be sufficiently high to reject it even were its expectation enormous. Answer by sampling equals, there is one mathematically correct answer with sampling by William Feller. Sufficient knowledge of probability theory and statistics is necessary to fully understand Feller's answer. However, it can be understood intuitively because it uses the technique to play this game with a great number of people, and to then calculate the expectation from the sample. According to this technique, if the expectation of a game diverges, the assumption that the game can be played an infinite time is necessary, and if the number of times of the game is limited, the expectation converges to a much smaller value. Finite St. Petersburg lotteries equals, the classical St. Petersburg lottery assumes that the casino has infinite resources. This assumption is unrealistic, particularly in connection with the paradox, which involves the reactions of ordinary people to the lottery. Of course, the resources of an actual casino are finite. More importantly, the expected value of the lottery only grows logarithmically with the resources of the casino. As a result, the expected value of the lottery, even when played against a casino with the largest resources realistically conceivable, is quite modest. If the total resources of the casino are $, then L equals floor, log 2, W is the maximum number of times the casino can play before it no longer covers the next bet. The expected value E of the lottery then becomes. The following table shows the expected value E of the game with various potential bankers and their bankroll W. A rational person might not find the lottery worth even the modest amounts in the above table, suggesting that the naive decision model of the expected return causes essentially the same problems as for the infinite lottery. Even so, the possible discrepancy between theory and reality is far less dramatic. The assumption of infinite resources can produce other apparent paradoxes in economics. In the Martingale betting system, A gambler betting on a tossed coin doubles his bet after every loss, so that an eventual win would cover all losses. In practice, this requires the gambler's bankroll to be infinite. The gambler's ruin concept shows a gambler playing a negative expected value game will eventually go broke, regardless of his betting system. Recent discussions, although this paradox is 3 centuries old, new arguments are still being introduced. Samuelson resolves the paradox by arguing that, even if an entity had infinite resources, the game would never be offered. If the lottery represents an infinite expected gain to the player, then it also represents an infinite expected loss to the host. No one could be observed paying to play the game because it would never be offered. As Paul Samuelson describes the argument, Paul will never be willing to give as much as Peter will demand for such a contract. And hence the indicated activity will take place at the equilibrium level of zero intensity. Ole Peters thinks that the St. Petersburg paradox can be solved by using concepts and ideas from ergodic theory. In statistical mechanics, it is a central problem to understand whether time averages resulting from a long observation of a single system are equivalent to expectation values. This is the case only for a very limited class of systems that are called ergodic there. For non-ergodic systems there is no general reason why expectation values should have any relevance. Peters points out that computing the naive expected payout is mathematically equivalent to considering multiple outcomes of the same lottery in parallel universes. This is irrelevant to the individual considering whether to buy a ticket since he exists in only one universe and is unable to exchange resources with the others. It is therefore unclear why expected wealth should be a quantity whose maximization should lead to a sound decision theory. Indeed, the St. Petersburg paradox is only a paradox if one accepts the premise that rational actors seek to maximize their expected wealth. The classical resolution is to apply a utility function to the wealth, which reflects the notion that the usefulness of an amount of money depends on how much of it one already has, and then to maximize the expectation of this. The choice of utility function is often framed in terms of the individual's risk preferences and may vary between individuals. It therefore provides a somewhat arbitrary framework for the treatment of the problem. An alternative premise, which is less arbitrary and makes fewer assumptions, is that the performance over time of an investment better characterizes an investor's prospects and, therefore, better informs his investment decision. In this case, the passage of time is incorporated by identifying as the quantity of interest the average rate of exponential growth of the player's wealth in a single round of the lottery. Per round, where is the payout, is the probability of receiving it, is the wealth of the player, and is the cost of a ticket. In the standard St. Petersburg lottery, and although this is an expectation value of a growth rate, and may therefore be thought of in one sense as an average over parallel universes, it is in fact equivalent to the time average growth rate that would be obtained if repeated lotteries were played over time. While is identical to the rate of change of the expected logarithmic utility, it has been obtained without making any assumptions about the player's risk preferences or behavior, other than that he is interested in the rate of growth of his wealth. Under this paradigm, an individual with wealth should buy a ticket at a price provided. This strategy counsels against paying any amount of money for a ticket that admits the possibility of bankruptcy, that is, for any, since this generates a negatively divergent logarithm in the sum for which can be shown to dominate all other terms in the sum and guarantee that, if we assume the smallest payout is, then the individual will always be advised to decline the ticket at any price greater than, regardless of the payout structure of the lottery. The ticket price for which the expected growth rate falls to zero will be less than but may be greater than, indicating that borrowing money to purchase a ticket for more than one's wealth can be a sound decision. This would be the case, for example, where the smallest payout exceeds the player's current wealth, as it does in Menger's game. It should also be noted in the above treatment that, contrary to Menger's analysis, no higher paying lottery can generate a paradox which the time resolution, or, equivalently, Bernoulli's or Laplace's logarithmic resolutions, fail to resolve, since there is always a price at which the lottery should not be entered, even though for especially favorable lotteries this may be greater than one's worth. Further discussions, The St. Petersburg Paradox and the theory of marginal utility have been highly disputed in the past. For a discussion from the point of view of a philosopher, see also, Ellsberg Paradox, Exponential Growth, Gambler's Ruin, Kelly Criterion, Martingale, Pascal's Mugging, Two Envelopes Problem, Zeno's Paradoxes. References and notes, citations. Works cited, Arrow, Kenneth J. The Use of Unbounded Utility Functions in Expected Utility Maximization, Response. Quarterly Journal of Economics 88, 136 138 doi, 10.2307/1881800. JSTOR 1881800. Handle, Repec TPRQJECONV88Y 1974 I1P 136-38. Bernoulli, Daniel. Originally published in 1738. Translated by Dr. Louise Summer. Exposition of a New Theory on the Measurement of Risk. Econometrica 22, 22 €36 doi, 10.2307/1909829. JSTOR 1909829. Retrieved May 30, 2006. Blavatsky, Pavlo. Back to the St. Petersburg Paradox. Management Science 51, 677 €678 doi, 10.1287/MNSC. 1040.0352. De Montmort, Pierre Raymond. Essay d'analyse sur les jeux de hasard, Essays on the Analysis of Games of Chance. Providence, Rhode Island, American Mathematical Society. ISBN 978-0-8218-3781-8. As translated and posted at Paulskamp, Richard J. Correspondence of Nicolas Bernoulli concerning the St. Petersburg game. Retrieved July 22, 2010. Laplace, Pierre Simon. Thar Copyright Théorie analytique des probabilités. Copyright S, Analytical Theory of Probabilities. Paris, V. Corsia. Martin, Robert. The St. Petersburg Paradox. In Edward N. Zalter. The Stanford Encyclopedia of Philosophy. Stanford, California, Stanford University. ISSN 1095-5054. Retrieved May 30, 2006. Menger, Karl. Das Unsicherheitsmoment in der Betrachtungen im Anschluss das sogenannte Petersburger Spiel. Zeitschrift für One-Quarter Nationale Paragraph Economy 5, 459 €485 doi, 10.1007/BF013115778. ISSN 0931-8658, Peters, Ole. Menger 1934 Revisited. Journal of Economic Literature. Peters, Ole. The Time Resolution of the St. Petersburg Paradox. Philosophical Transactions of the Royal Society 369, 4913 €4931. doi, 10.1098/RSTA. 2011.0065. Pianca, Paolo. The St. Petersburg Paradox, Historical Exposition, An Application to Growth Stocks and Some Simulation Approaches. Quaderni di Didattica, Department of Applied Mathematics, University of Venice 24, 1 €15. Rieger, Mark Oliver. Wang, Mary. Cumulative Prospect Theory and the St. Petersburg Paradox. Economic Theory 28, 665 €679 doi, 10.1007 per second 00199-005-0641-6. ISSN 0938-2259, Samuelson, Paul. The St. Petersburg Paradox as a Divergent Double Limit. International Economic Review 1, 31 €37 doi, 10.2307/2525406. JSTOR 2525406. Samuelson, Paul. St. Petersburg Paradoxes, Found, Dissected, and Historically Described. Journal of Economic Literature 15, 24 €55. JSTOR 2722712. Todhunter, Isaac. A History of the Mathematical Theory of Probabilities. Macmillan and Company. Tversky, Amos. Kahneman. Advances in Prospect Theory, Cumulative Representation of Uncertainty. Journal of Risk and Uncertainty 5, 297 €323 doi, 10.1007/BF00122574. Bibliography Oman, Robert J. The St. Petersburg Paradox, A Discussion of Some Recent Comments. Journal of Economic Theory 14, 443 €445 doi, 10.1016/0022-0531, 77, 90143-0. Durand, David. Growth Stocks in the Petersburg Paradox. The Journal of Finance 12, 348 €363 doi, 10.2307/2976852. JSTOR 2976852. Feller, William. An Introduction to Probability Theory and Its Applications Volume I, 2. Bernoulli and the St. Petersburg Paradox. The History of Economic Thought. The New School for Social Research, New York. Retrieved May 30, 2006. Hay, John. Taking Chances. Oxford, UK, Oxford University Press. Pages 330. ISBN 0198526636. External links, online simulation of the St. Petersburg Lottery.